So good morning to all. So this is Selvakumar from SNS College of Technology and Department of Computer Science Engineering. So now I am going to tell about memory management concept, but the topic of structure of the page tables. So structure of the page table. So in a structure of the page table, so in a memory, so we consider some memories, and in a memory, the structure for paging can get queues using straightforward methods. So the memory in a memory, the structure considered a 32-bit logical address space or in modern computers. So in a page size of 4 kilobits, it means 2 per 12 bytes, and a page table would be a 1 million entries, 2 per 32 divided by 2 per 2 per 12. If each entry is a 4 byte, it is a 4 MB of physical address is used in the page table alone. So that amount of memory used to cost a lot. So that we don't want to allocate that contiguously in the main memory. So in a page table, we are using a hierarchical paging and hashed page tables and inverted page tables. So first thing, hierarchical page table. So in a hierarchical page table means it is a break up the logical address space and into multiple page tables. So in a it is a simple technique is to a two level page tables, and then the page table is in the page table. This is two level page table. So we have a outer page table and a page table and a memory. So in a outer page table we consider a number of tables. In a page table we consider the base address and limit address. The each and every address transferred to the main memory. So two level paging example. So in a logical address is divided into two things. One is a page number consisting of 22 bits, and another one is a page is consisting of 10 bits. So since the page table is page, the page number is further divided into two things. One is a 12-bit page number and a 10-bit page offset. Thus a logical address follows. So page number P1 PD and the page table is offset D. So P1 contains 12 and P2 contains 10. The page offset is D. So where P1 is an index into the our outer page, the table, and P2 is the displacement within the page of the inner page table. So this is known as a forward mapped page table. This is the how the page table can be worked in a logical address to physical address. So this is an address translation scheme. So we have a logical address called P1, P2 and offset D. So when the outer the P1 is moved to the outer page table, and then outer page table then moved to the page table of P2, and then P2 is considered continually transferred to the offset D. So we have 64-bit logical address space. So even two level page scheming are not sufficient. So for meaning it means if a page size is a 4 kilobyte, the page table has 2 per 52 entries. If a two level scheme means if the inner page table could be a 2 per 10 4 bytes entries. So for example, address would like to be outer page P1, outer page P2 and offset. So we have a 42 pages in P2 and 10 pages to P2 and D12 for D offsets. So outer page table has a 2 per 42 entries or a 2 per 44 bytes. So one solution is to add to second outer page table. So but in the following examples, the second outer page table is still 2 per 24 bytes in a size. So and also it is possible for memory access to get the one physical memory location. So this is a three level paging schema. So we have a two level at outer pages and inner pages and offset. So we have a three level paging schema. We have a second outer page and outer page and inner page and offset. So we have a P1, P2, P3 and a D is an offset function. This is a hashed page table. So the hashed page table commonly used in address space of 32 bits, and the virtual page number is a hashed in the page table. So this page table contains a chain of elements and hashing to the same location, and each element contains in the virtual page number and the value of the mapped page frames. So the third one is a pointer to the next element. So next one is the virtual page number are compared in the client chain searching for a match. It means if a match is found, the corresponding physical frame is extracted. So the variation of 64-bit address is clustered page table, and it is similar to hashed, but each entry refers to several pages, such as 16, so rather than one. So in this page, especially useful for spaces, sparse and address pauses. So when the memory references are non-contiguous and scattered. So this is the hash table function. So we have a logical address called as a P and D and a physical address called as a R and D. So in this to the physical memory. So we have a hash function called a hash table. The hash table should move to the Q and S and the PRS. The Q and is a Q and star, and Q and S is transferred to the P. So the P is sent to the R level. So base and limit address are added to the physical address, and then it is transferred to the physical memory. So inverted page table. So rather than each process and having a page table and keeping track of all possible logical bases and track all physical pages, that is called inverted page table. So it means one entry for each real page of memories. So this is the main condition. So entry consists of the visual address of the page stored in the that real memory location. So with information about the process that owns the pages. So the inverted page table to decrease memory needed to store each page's table, but increases time needed to search the table within a page reference request. And also its use has to table in a limit the search to 1. So at a most of the few and the few tables are entries. So it contains a TLB can accelerate accesses. So how to implement a shared memory means, so one mapping of a virtual addresses to the shared physical address spaces. So this is the Oracle Spark Solaris. So consider modern 64-bit operating systems example with a tightly integrated hardware. So we as the goals are efficient and low overhead. So based on hashing and mashing, it is more complex. So we have two hash tables. One is kernel and one for all process. And each map is address from a virtual physical memory. So each entry has a based address and span and indicating the memory of the pages in the entry represented. So Oracle presents the table virtual address TLB holds a translation that entries of all past hardware lookups. Virtual address reference causes TLB search. So if a hardware walk in the memory, so TSB looking for the TTI corresponding to the address. If a match found, the CPU copies the TSB. If no match found, if the kernel interrupted to search the hash tables. So this is my reference. Thank you.